Hello everybody, my name is Peter Wilson, and this is a video lecture to accompany section 11.2 in the textbook, and this is Astronomy 201 at Medicine Hat College. And this section we're going to be talking about the giant planets. Okay. The basic characteristics of the giant planets. The giant planets are further from the Sun than the terrestrial planets, obviously. Jupiter orbits at 5 astronomical units with an orbital period of 12 years. Saturn orbits at 10 astronomical units with an orbital period of almost 30 years. Uranus at 19 astronomical units has an orbital period of 84 years. And Neptune at 30 astronomical units takes 165 years to orbit the Sun. Jupiter and Saturn, the gas giants, have many similarities, although Jupiter has 4 times the mass of Saturn. Uranus and Neptune are quite a bit smaller and have significant differences in structure and composition compared to Jupiter and Saturn. Jupiter's diameter is 11 times that of Earth, which means it has 1,331 times the volume, but Jupiter only has 318 times the mass, which means that the density is only a little over 25%. In fact, I don't even know if it's that, but the low density alerted early scholars of the solar system to the fact that Jupiter is largely composed of hydrogen and helium gas. And just a little sidebar here, the universe is composed of 75% hydrogen and 25% helium, and everything that's not hydrogen and helium in the universe is what happens when you take 100% and you subtract 75% and then you subtract 25%, which means that it's just a little tiny wee bit. So everything that we see around us, all the rocks and metals and earth and dirt and people and trees and crap, that's tiny percentage of the mass of the universe. Yeah, okay. Saturn's density of 0.7 grams per cubic centimeter is just over half of that of Jupiter's at 1.3 grams per centimeters cubed. Saturn is light enough to float, if you can imagine a bucket of water big enough to float it in. Uranus and Neptune are only about 5% as massive as Jupiter, but they have similar densities. And this is a clue that their composition is quite different, because with a similar composition with much less gravity, their density would be much less than Saturn's. And there's many known exoplanets that are similar in size to Uranus and Neptune. In fact, with exoplanets, they talk about Neptunes and they talk about Jupiters, which means planets of similar size and presumably similar properties. Okay, so appearance and rotation. The giant planets do not have solid, well-defined surfaces like terrestrial planets, and their gaseous atmospheres are simply a less concentrated extension of their gaseous bodies. The uppermost clouds on Jupiter and Saturn are composed of ammonia crystals. On Neptune, the clouds are made of methane. Uranus has no obvious clouds, just a featureless haze. Visually, Jupiter is a very colorful and dynamic planet. Features in the atmosphere allow a determination of the rotational period of the atmosphere. However, the atmosphere of Jupiter doesn't rotate at the same speed as a planet. In fact, the planet, being a fluid composition, doesn't rotate like a solid body. It exhibits differential rotation, which basically means that the core rotates at one speed, and the equatorial region rotates at a slightly different speed. And yeah, and every part of the planet is rotating at a different speed. The rotation of the core, which is determined by the rotation of the magnetic field, is taken as the rotational period of the planet in 9 hours and 56 minutes, which is the shortest rotational period of any of the planets in the solar system. Saturn's rotational period is slightly longer at 10 hours and 40 minutes. Uranus and Neptune have longer rotational periods of about 17 hours. So seasons, we know, are caused by the inclination of the planet's axis, and Jupiter with an inclination of 3 degrees has no seasons. Saturn with an inclination of 27 degrees has Earth-like seasons, as does Neptune with an inclination of 29 degrees. Although, of course, since nobody lives or could live on either on gas giant. The concept of seasons isn't quite the same as it is on Earth. And Uranus is the oddball of the bunch with an inclination of 98 degrees. And Uranus lays on its side with its rotational axis 8 degrees below the plane of the solar system. And so this is an infrared image of Uranus taken by the Hubble Space Telescope. And the interesting thing is the 5 reddish clouds. The 5 reddish clouds, what was I reading at? The 5 reddish clouds can be seen to rotate around the parallel to the equator. What the hell is that saying? I have to read that again. Oh, I think they're missing the word. I think what that's supposed to say is the 5 reddish clouds can be seen to rotate around the planet parallel to the equator. That makes more sense. So the white line is the equator, and here are the clouds for the first picture, and you can see in the second picture the clouds have moved a little bit. Appear to have moved a little bit. And the rings, which are faint and visible light but prominent in infrared, and 8 moons can be seen rotating around the equator, around parallel to the equator. Okay. So much for Uranus. Now, the fact that the rotation of Uranus just plays havoc with the day-night cycle on the planet, because if you look over here in 2028, when the North Pole is facing the sun, if you're at the North Pole, you see the sun directly overhead. For quite a few years, the sun would be directly overhead. There's no day, no night at all. If you lived on the South Pole, you would never see the sun, so it'd be continuous dark again for many, many years. If you live on the equator, the sun would be on the horizon. Yeah. Yes, that makes sense. The sun would always be sort of in the same point. Now then in 2049, when Uranus is moved to here, the sun is going to be around the equator, and you're going to have a normal day-night cycle. Every rotation of the planet, you're going to have day and night. And then in back in 1986, because now we're going to go back into a previous orbit, the South Pole faces the sun, and the South Pole has continuous daylight, and the North Pole never sees the sun. And so you can see sort of how that works. And this is this graph is showing the amount of sunlight that's seen at the poles and at the equator during the planet's orbit. So at the equator, see a lot of sunlight, then no sunlight, then a lot of sunlight, then no sunlight, then a lot of sunlight. And of course, a lot of sunlight would be in 2007 and 2049 when the sun is over the equator. And at the South Pole, that would be from on the right side of the orbit when the South Pole is facing the sun, and then on this side would be the other side where the South Pole is facing away from the sun. Yeah, so you can sort of see how that goes. Okay, so it's unknown what caused Uranus to be tipped on its side. Textbook theorizes giant impact as the planet was forming, but would that explain why the moons and the ring rotate in the plane perpendicular to the ecliptic? And it's interesting that Pluto shares the same rotation, which is also interesting. And so basically not really knowing why that happened. Perhaps the path of wisdom is just admit ignorance and move on. So, as mentioned earlier, the mass and density of Jupiter and Saturn can only be explained in terms of a composition of the light gases, hydrogen and helium. But deep in the interiors of these planets, gases are very easily compressed, and they're very large planets, so in the center of the planet there's a great deal of pressure and there's a great deal of compression, and the gas is so highly compressed that its behavior is very different from what you might expect. Theory predicts a central pressure for Jupiter that's larger than 100 million bars, 100 million Earth atmospheres, and a density of about 31 grams per cubic centimeter, as compared to the density at the center of the Earth, which is about 13 grams per cubic centimeter, and that is composed of iron and nickel. And Jupiter has a much larger density, and it's hydrogen and helium. So 24 times the central pressure and twice the central density of the Earth's core, and Earth's core is composed of heavy metals. At a few hundred kilometers into Jupiter and Saturn, the gas condenses into a fluid. At a few thousand kilometers, the hydrogen becomes metallic. And metallic hydrogen is what physicists would call a plasma. The electrons and the protons become disassociated and can move independently. And when that happens, then the protons and the electrons are both charged particles. They become electrical conductors. And so you have an electrically conducting fluid in the interior of a rapidly rotating planet. And the result is a massive magnetic field. Okay. Saturn has so Jupiter's interior is mostly metallic hydrogen. Saturn has a substantial amount of metallic hydrogen, but most of its interior is liquid hydrogen. And Uranus and Neptune are too small to liquefy hydrogen. Each of these planets, the authors believe, have cores consisting of ice and rock, where ice refers to compounds of carbon, nitrogen, and oxygen. And Uranus and Neptune are believed to have mantles that are primarily composed of ice. There's a bit of an issue about whether Jupiter has a metallic core or not, but or an icy, rocky core, I guess I should say. That's a bit of a controversial, but the authors of the textbook have, for reasons of simplicity, chosen to ignore that controversy, and so we won't talk about it anymore. Okay, so these are like little sort of samples going down into the planet's interior for Jupiter and Saturn. And you see rock at the bottom, and then a layer of ice, and then a layer of metallic hydrogen, and then a layer of molecular hydrogen on top. For the much smaller planets, Uranus and Neptune, you see rock at the core, and then you see a layer of ice, and then you see the molecular hydrogen on top of the ice. Okay, yeah, and this image of the south polar region of Jupiter was taken by the Juno mission. I'm not sure why that's here. We've already seen this in a previous lecture. Okay, internal heat sources. The authors believe that rocky icy cores formed first from the solar nebula, and then the gas was gravitationally captured. Jupiter, Saturn, and Neptune all have internal heat sources in that they emit more heat than what is incident upon them. And Jupiter's heat source is gravitational potential energy left over from its formation that is still slowly escaping into space. So much like Earth, Jupiter still has a very hot core, and the energy from the core is, and because of course since Jupiter doesn't have a crust, there's no rock to impede the flow of the heat. The heat flows freely into the gas in the atmosphere, except that it's such a large planet that it takes a long time. Okay. And when I say the authors believe that the rocky icy cores formed first from the solar nebula, that might not be the controversy. I said we weren't going to say anything more about it. But what the controversy is all about is the formation of Jupiter. And Jupiter might not have formed the core first. The the entire planet might have, the gas might have been what sort of amalgamated. No, I don't know what the term is. The gas planet might have formed first, and then if it has a core, the core might have settled out of the gas, which is an issue that's still not entirely resolved. Okay, so we talked about Jupiter's heat source, so it makes sense that we're going to talk about Saturn's heat source. And Saturn's heat source, they like to call that helium rain, which is kind of a sort of poetical sound. You know, you're outside and the helium rain is slowly falling. But it's really what it is, a condensation of helium. They, at a certain place inside the planet, the pressure and temperature is right for helium gas to condense into a fluid. And then when it condenses into a fluid, it's denser than the surrounding gas, and it falls into the planet's interior. And as it falls, that's there's two things. The condensation of the gas generates heat, and as it falls into the planet, there's a loss of gravitational energy as it falls, which is also converted into a heat. And this is an example of ongoing differentiation. As helium, the heavier gas, heavier than hydrogen, condenses out and sinks to the core. Neptune's heat source is a complete mystery, but it is sufficient to maintain a similar atmospheric temperature to Uranus, although Neptune is almost twice as far from the Sun. I don't know if that's quite true. I'd have to look back to know if that's true. I think that we can look back and check that, actually. Somewhere back here. A lot farther back. So, well, it's not twice as far, but it's not far from twice as far. It's 19 astronomical units and 30 astronomical units. So, of course, 15 astronomical units is half of 30. So it's, now we can easily say 1.5 times as far anyway. Okay, where were we? Way down here. Okay, so Neptune's much further from the Sun, but it has a heat source that keeps the atmosphere at a similar temperature to Uranus. Okay, each of the giant planets have magnetic fields caused by flowing electrical currents in its interior. Associated with the magnetic fields are the magnetospheres that surround the planet. Excuse me, I just got to burp a little bit there. Jupiter, with its rapid rotation and vast body of metallic hydrogen, has a huge magnetic field, almost 20,000 times that of the Earth. Saturn's field is about 600 times Earth's field, which is much, much smaller than Jupiter's field, obviously. And Uranus' field is about 50, and Neptune's is about 30 times that of Earth. And so this is Jupiter in radio waves. So this is Jupiter in at radio wavelengths, and what you're looking at is the magnetosphere. Yeah. So that's kind of interesting, I guess. Anyway, next. Now, if we were to ascribe the magnetic field of a planet to its rotation, then we would expect that the magnetic field will line up with the planet's rotation axis. This is the case with Saturn, but we have already seen that's not the case with Earth. Earth is close, but it's several degrees off. Jupiter's field makes an angle of about 10 degrees with the rotation axis. And those are close to what you'd expect, although obviously not exactly what you'd expect. But Uranus and Neptune are very divergent, with Uranus's magnetic axis about 60 degrees away from the rotation axis, and Neptune's by about 55 degrees. And these divergences are not understood. I mean, it's a complete mystery. The only spaceship that's ever been out there is Voyager 2, so all we know is what we got from Voyager 2, And there's just no explanation for this type of craziness. That's just crazy. And so this is a NASA image demonstrating that. And not only do the magnetic fields not line up with the rotation axis, in Neptune's case, well, actually in both cases, the magnetic field, oh, I guess no, that's not quite true. In Neptune's case, the area where the field is generated doesn't even lie on the rotation axis of the planet. I guess in Uranus's case it does cross the, you can see it crosses the rotation axis. So then it's, anybody's guess as to how that happened. And I could offer a guess, but my guess would be as uninformed as anybody else's. So that concludes the video lecture to accompany section 11.2 in the textbook. And goodbye.